Greetings, everyone. I have a new series planned out for you called Modulo, in which I'll describe several fascinating theorems of number theory that are based around this concept. What you'll discover is that many mathematicians were pondering these patterns in the 18th century, which is really not so long ago in the history of mathematics. And as you'll see, an important milestone came in 1801, with the publication of a book by my personal favorite mathematician, C.F. Gauss. And, by the way, this source, at which you're currently looking, is a paper from the math department at Cornell University. It's really quite well done. And there's another source called storyofmathematics.com, and it's something I recommend very much for your own personal use. After all, mathematics really is a story, as I see it. And this story has indeed lasted hundreds of years, so why not learn as much as we can? Just imagine, the ideas I'm about to present to you in this series, and in many other series as well, are the exact same ideas thought by mathematicians in the pre-industrial revolutionary era. So mathematics truly transcends one's time, place, and even language. But whether you're a newcomer to my channel or a long-time viewer, young or old, please allow me to guide you through this multi-part journey dedicated to modular arithmetic. Now, modulo, often abbreviated mod in mathematical language, represents the idea that we are dividing one integer by another integer and taking the remainder. So, just to see certain examples, and by definition what this is saying is that a minus b is some integer evenly divisible by n. And so I'll show you some more concrete examples just to show what I really mean by that. So we can pronounce it a is congruent to b modulo n, and we can call b the residue of a modulo n, and we can also write it in this notation. But usually you'll see, just to see some concrete examples, you'll see this format, which is, let's say, 5, and we're comparing it to 3. So we're saying, what is 5 modulo 3? Well, in this case, we really want to find the number, the integer, from 0 to 2, that satisfies the equation, where basically 5 minus this number, right here, is evenly divisible by n, or 3 in this case. And so, I'm sure you can imagine already that the solution in this case would actually be 2. That is because, 5 minus 2 is equal to a multiple of 3. And another example would be 17 is congruent to, and I'm going to say modulo 2, and it is actually congruent to 1 modulo 2. And what this is really saying, in fact, whenever you see modulo 2, really what that's doing is determining whether a given integer, usually the one on the left side right here, determining whether that integer is even or odd. For instance, if we had a number which is congruent to 0 modulo 2, that means that the number minus 0, really just the number, is evenly divisible by 2, which means it's really even. However, saying that it's congruent to 1 modulo 2, is just saying that it is odd. And then, of course, we have the example 4 is congruent to 0 modulo 4. That one's pretty basic. 4 is already itself divisible by 4. And you'll likely hear people referring to this as some kind of clock arithmetic, because similar to the way an analog clock works, if you get a number sufficiently large, that is kind of beyond the upper bound, say, let's say, 13 on a 12-hour clock, that number kind of wraps around the system, and you end up with 13 modulo 12, which is really 1. So, it's the same idea that you never hear people really saying 13 o'clock. That would be a little bit silly, unless we're talking about military time. You might say 1300 hours, but even so, if you consider that, even in military time, you wouldn't have anything larger than 2400. Or, well, actually, you wouldn't even have that. You wouldn't have anything greater than 2359, to be more accurate. So there is an upper bound when we're measuring time, which makes sense because time is cyclical in some sense. And it's the same idea in modular arithmetic, and it becomes very useful, especially in things like finite fields, which are beautiful examples of number theory, which really more people should know about. More people should appreciate it. And again, we'll get to that later. Well, we'll get to the actual theorems and why they're actually beautiful, why they're wonderful later on. But just for now, realize that the only relevant numbers in some kind of modular system are really the natural numbers 0 through n minus 1. And so what I mean by that, just to show an example, if we were in mod 4 arithmetic, modulo 4 arithmetic of some sort, the only numbers you'd find in this second kind of variable position, so to speak, the only numbers you'll ever find there in modulo 4 arithmetic would be 0, 1, 2, or 3. Since, and you know, the reason for that is that every multiple of 4 is really defined to be 0. Because it's, you know, it's already divisible by 4. So that's the way we're thinking in modular arithmetic. And usually in these theorems, which we're about to see, we're actually going to end up seeing many variables in these equations. And I'm probably going to say them as A is congruent to B modulo n. Or something of that format. Sometimes n is replaced by p, because usually it can be a prime number, which is actually very interesting. But I just wanted to go through some of these more basic properties of modular arithmetic, which are listed right here in this Cornell University document. So the first thing here is it says a number and its negative are usually not congruent, and that might already be obvious, but even if it's not, I mean, for instance, you know, 1 typically isn't even equal to negative 1. That typically wouldn't make much sense. And even in the modular arithmetic world, it usually doesn't make sense. I can think of only one case where that would be true, and that would be mod 2. But anyways, a point I'd like to make about this is how to deal with negative numbers in modular arithmetic. But I'll do that in a quick video, which you can see right here. I might make it an unlisted video or just a public video, but I'll link to it right here. I just have a quick note about that. But even so, we see the properties of equality in modular arithmetic, and we know that if A is congruent to B and C is equal to D modulo n, then we can combine those in various ways. We can say that A plus C must be equal to B plus D modulo n, and that A times C is congruent to B times D modulo n. But as this source describes very well, dividing is not as simple. You know, we can say that 36 is congruent to 6 modulo 10, but dividing by 2 would, if we did a similar thing, if we tried a similar thing, we would simply have 3 is congruent to 18 modulo 10, which is clearly not true. And so we can do two different things, two possible operations with division, and that is that if we're dividing by a number k, which is relatively prime to n, meaning that basically k and n share no proper divisors, so basically the greatest common factor is 1, then we can effectively divide this through just by dividing a and b. So, for instance, it says dividing by 3 would work successfully, because 3 and 10 don't share a common factor. After all, 3 is prime, and it doesn't divide 10. And so that one does work. We get 2 is congruent to 12 modulo 10. However, the next one, the next rule, it says that if we divide all three numbers, a, b, and n, by a number which is a divisor of n, so 2, for instance, if we're dividing by 2, well, 2 is a factor of 10 here. So we need to divide on through, like a, b, and n need to each be reduced. So we're dividing by 2, giving 3 is congruent to 18 modulo 5. So this is just setting up the basics of how division works in modular arithmetic, which is quite interesting. And so thanks very much for watching. If you have any questions, let me know. And yeah, I'll see you later.